Hello again, your friendly heavy physics teacher here. This is a college physics lesson for my college physics class. Like it'd be for anybody else, unless you're one of my few members of the public who are watching this just because. All right. This is for Unit 11, Lesson 5.2. Um, uh, this is the second part of the notes that I sent out via email. I'm actually going to send out an additional version, which is much more details, covers much more details about what we're covering with this particular lesson. In this lesson, we are going to talk about how waves on a string make sound, how the waves in the string are behaving in order for the sound that they result from uh, um, happens. We're also going to talk about windpipes. Windpipes are anything from flutes and brass instruments like trumpets and trombones to physical windpipes, the kind of things that are on the wind chimes, pan pipes, organ pipes. These are all forms of what I call windpipes, and how they use the same principles that we find in waves on a string, and what we call harmonics. All right, and harmonics are how you can get waves to happen within the same dimensions as a fundamental wave. All right. All right. What we're talking about here is when anything is caused to vibrate, be it from a tall skyscraper, a bridge, a piece of string that your clothing might be hanging on, um, the water waves within a harbor, uh, musical instrument strings, the pipes, or even a wine glass. All vibrate at a particular natural frequency based upon their shape, based upon their dimensions. So you can do this, and you can hear that tone. I'm exerting a force on the side of the wine glass, and it's creating a tone based on that. Interestingly enough, you can use a different form of friction. There we are. That tone right there, I know some of you find that annoying. Me, I'm ambivalent about it. In the same way that screeching chalk on the chalkboard doesn't always annoy me. All right. Notice that that tone is essentially the same as that tone. Okay. And that's because everything based upon its elastic properties will have a natural frequency at which it vibrates, a fundamental frequency based upon the physical dimensions of the thing that is vibrating. Okay. If you were to produce another tone that was exactly the same frequency as that, this would start vibrating. I can't sing high enough, I can't sing a note high enough that would cause that to vibrate. All right. Um, uh, that, when you do that with another sound wave and cause something else to vibrate, that's known as resonance. That's what we were talking about the other day. Okay. So, how is the sound being made from the waves that are actually physically inside moving around this glass? It's the same way for stringed instruments like a guitar, piano. It's the same way for wind instruments. such as clarinets or flutes or trombones or trumpets. Okay, all of them have the same principles on which to determine the basic tones that you can make with them, and then the higher tones that can result from those basic tones. Okay, now that basic tone, that basic wave that can vibrate in the material, be it a glass, be it a string on a guitar, whatever you have moving around, um, there is a natural, fundamental frequency at which that will happen. Okay, so we're going to call that natural frequency. All right, natural frequency is the basic or the lowest frequency that the physical object can vibrate at based upon the elastic nature of that object. You get the wind blowing on a building, and if it had no other things other than the structural parts of the building, you would feel, if you were at the top floors of the building, you would feel that vibrating back and forth rather strongly. All tall skyscrapers are built with dampening pendulums inside them, so that as the building would begin to vibrate, the pendulum actually, its inertia moves in the quote unquote moves in the opposite direction, dampening that vibration, so that very tall skyscrapers having a natural frequency, we reduce the amplitude of that swing. Doesn't totally eliminate it, but it reduces it significantly. Okay? So if we don't reduce it, if we just let it happen, for instance, a guitar string, pluck it, strum it, and it naturally vibrates at a particular frequency. That frequency depends on how fast the wave is moving in the object, how fast it's moving in the string, and what the wavelength is for that string. Okay? Okay, so the speed of the wave in a string, or a wire, or any other vibrating linear object that has a strong tension on it, all right? The speed of the wave moving back and forth through the string itself, not out here in the air, but in the string itself, the speed of the wave in the string is equal to the square root of the force of the tension on the wire or string or clothesline, whatever it happens to be, divided by this linear density here, mass per unit length. Okay? And it is this length that is going to determine what the wavelength is. Okay? So the speed of the wave from that other equation, all right, F natural equals V divided by wavelength. The V here for a string is dependent on how much force, how much tension is on the string, and the mass per unit length of that string. And that's the reason why the G string on a guitar is the lowest string, is the lowest sound, even though all the strings on the guitar have the same length. If you look at them, and you guitarists, you all know about this already, but if you look at the strings on a guitar, you'll notice that the high note strings all are very thin, and the low note strings are thick. Some of them appear to have wire wrapped around them, okay? And that means that the thicker the wire is, the more mass it has per unit length, it's going to vibrate more slowly, all right? It's not going to vibrate as quickly. The speed of the wave moving back and forth through the length of the string that's on the guitar is moving more slowly in the lower wavelength. It's moving more quickly in the higher wavelength. Or I should say, moving more slowly in the lower frequencies and moving more quickly in the higher frequencies. Okay? Now, what determines the wavelength of those strings? So physically, it's quite literally the length of the string on the guitar, okay? Or the length of the string in the piano, the length of the string on the bass, the length of the string on whatever instrument is vibrating, okay? And the shortest wavelength that can happen in that is the one that has a half wavelength vibrational mode for the length between the attachment points of that string. Okay, so here's our guitar, and here's the bottom attachment point. Here's the top attachment point at the end of the fretboard. Okay, and when you pluck the string, when you flick on the string, it will naturally vibrate like this. You see it going back and forth. Okay, that is a half wavelength because here's a node, here's the antinode, and there's the node. Now, if you'll recall from my previous lesson, and you know that the wave is traveling back and forth through the string, okay? And because of the tension and because of the elastic properties, that wave is bouncing off of these 2 points. These are rigid boundaries. Well, remember that as the wave comes into here, it's going to send its amplitude in the opposite direction, creating a node for this interference right here between the incoming wave and the reflecting wave. In the middle here, we've got an antinode, all right? This is where the reflected wave and the incoming wave, the incident wave, the one that's reflected off of this boundary, the two of them meet, and they will always be in the same direction. And that's why we get this vibration up and down in the middle of the string. And at the ends, we have nodes, half wavelength, okay? Because if I were to extend the picture over here, notice I would get the full wavelength over here. This distance over to here is 2 times that distance right there. So the wavelength for the fundamental wave is 2 times the length that is able to vibrate within that. And that's why we call it vibrational length. Okay? The vibrational length is not the wavelength. The vibrational length is the physical dimensions in which the material can vibrate. Okay? So, fundamental frequency happens at a wavelength that is twice the length of the vibrational length of the instrument. Okay? That's why ukuleles have a higher sound than guitars in general. All right? Yes, the other factor that's going to affect that. Notice that with 6 strings on a guitar, the higher note strings are going to be lighter. They're going to have less mass in that length. The low note strings, the thicker the string, they're going to have more mass in that length. So the speed of the wave in the high strength, the low mass strings is going to be moving faster back and forth than in the low mass, okay? All of them have a certain tension on them, which is why tuning the string depends on the tension of the string, all right? You're up here, you pluck that and hey, I'm sounding a little flat. That means that the string isn't vibrating quick enough because for that wavelength, the frequency is going to be low because of the lower speed of the lower tension. All right, so you tighten it up a little bit and you pluck it, and now the tone is going to be higher. Same wavelength, but because the tension is higher, the speed will be higher, and if the speed is higher, the frequency will be higher. And so that's how you get your guitar making notes. That's how you get a bass making notes. It's a combination of the tension creating a certain speed to go through the string, the speed and the wavelength determine what that frequency is going to be. Now that frequency vibrates the air molecules around it. The air molecules then pass that frequency out to you. Dun, 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 dun. You hear the sound because that energy from the vibration of the string is going out here into space. The energy of the wave, the guitar string, isn't vibrating your ear, it's vibrating the air molecules, and that energy passes through the air molecules to your ear, which then vibrates the eardrum in your ear. Okay? Now, more than one vibration can happen within this same length. This is the fundamental vibration node. This is the lowest basic sound that can be made with these. Okay, I've watched guitarists do this, and it's pretty interesting. They will self-tune a guitar to itself. They will determine which string they want to use as their tuning string. Usually it's the low one because it's the easiest one to tune for them. And then based upon that, they will move to a point on that guitar string, pluck it, and then pluck the next guitar string next to it. And they will tune to the two of them. And the reason that they're changing their location of plucking it on the other guitar string is they are creating a harmonic. Okay? They are forcing that string to vibrate in a mode other than the fundamental frequency. They are forcing it to vibrate in a shorter wavelength within the same physical vibrational length. And this is called harmonics. All right? Harmonics are the higher frequency waves that can vibrate within the same vibrational length as the natural frequency. Okay? So let me go back to that other picture. The next higher length that can vibrate in this would be one where the vibrational mode would be a full wavelength, not a half wavelength, but a full wavelength in here. You see that? Okay. On the notes, you'll see the visualization technique that you can use to see how the harmonic vibration can fit within the same wavelength. So here we have the first half wavelength. At the second half wavelength, it's actually, if you multiply by 2, that's a full wavelength within there. The third harmonic, or the second overtone, would be the one that has 3 humps in here. All right, 2 up and 1 down. The fourth harmonic would be 2 full wavelengths within that dimension. Notice that the length, the vibrational length, isn't changing. The instrument isn't changing. But if instead of plucking up here on the guitar, we were to pluck, say, down here or maybe up here, we would force that to vibrate. Here would be my antinode. Okay? And with that antinode, all right, that would create a different wavelength within the same vibrational length. Okay? And so the harmonics are those higher wavelength, higher frequency, shorter wavelength, higher frequency vibration modes that can happen on the same string. These overtones, these harmonics, are what contribute to the sound quality. Okay? The purer the tone, the fewer harmonics are in that tone. Our vocal cords can either vibrate very purely, creating one frequency of vibration, or sometimes we can, depending on how we shape our vocal cords, we can create overtones where it creates a richer quality of sound because you're creating some higher frequency tones on top of the fundamental one that your vocal cords normally make. Same thing can be done for almost any instrument. So, back to our harmonic picture here, our harmonic notes, okay? The harmonics within a particular vibrational length create what we call overtones, okay? So the first overtone is actually the second harmonic. The first harmonic is the fundamental frequency. The second harmonic is the first overtone. It's the first doubling of the frequency. Second harmonic is the doubling of the first natural frequency. Third harmonic is the tripling of the first harmonic or the natural frequency. All right. Fourth harmonic is the quadrupling of the frequency. Okay. Now, first harmonic is zero overtone. Second harmonic is first overtone. Third harmonic is the second overtone. Notice there's that, you got to kind of subtract one from the harmonic to get which overtone it actually is. Okay? These happen at every half wavelength multiple for a string. For a string. Okay? They represent the multiple of the natural frequency. So your first harmonic is the fundamental frequency. Your second harmonic is the multiple, the first multiple of the natural frequency, or it's a doubling of the frequency. So it's 2 times Fn. The third harmonic would be the third multiple of the natural frequency. So it would be 3 times the fundamental frequency. You see how that works? Okay? Finally, I need to talk about windpipes, because windpipes use all the same way of figuring out what's happening with them. Okay? But with a windpipe, instead of the ends being where the reflection happens and the amplitude switches, the ends are open. The ends are non-rigid. So if your vibration source is over here, for instance, on a brass instrument, this would be where the mouthpiece is, and the brass player is vibrating their lips. For a flutist, they would be blowing across this, and the turbulence created by that air going across is creating the vibration source here. For a whistle, all right, or for a clarinet, this would be where the reed is vibrating at the one end of the clarinet, and down here is the bell of the clarinet. Okay, here is the bell of the trumpet. Here is the bell of the trombone. Here is the end of the flute. You'll notice that the end of the flute is always open. Okay, and so the fundamental frequency that happens within that is the one that has a node in the middle rather than an antinode. The antinodes are at each end because the wave reflects back on itself in the same direction. And so this wave coming through is going to create an antinode with the reflected wave coming back at this point. Okay? So, how is the speed of wave produced in a windpipe? Well, it depends on air. All right? Unlike a stringed instrument, where the thing that is vibrating, the thing that has the wave passing back and forth through it, is a solid piece of matter. Here we've got a gas. The gas is air. And so the speed of the sound in air depends on the temperature of the air. Okay? So the ambient speed of sound is equal to 331 meters per second at 0 Celsius, 331 meters per second, plus or minus, okay, this factor times the current air temperature. So for most rooms, air temperature is 20 degrees Celsius, give or take a degree, all right? So at 20 degrees Celsius, that makes this 12, a factor of 12. So you would add it to this. So for the speed of sound right now in your room, the speed that the sound is coming out of the speakers of your laptop to your ears is about 343 meters per second, not 331. This is how you determine that V in this original equation. Notice that I put it as V ambient here rather than just a regular V. The length, the wavelength, is still determined using 2L, okay? Harmonics and overtones still obey the same half wavelength multiple principle as this, as a stringed instrument. It's just that for a windpipe, the ends are open rather than closed. For strings, the ends are closed rather than open because of the way the wave has to reflect off of the boundaries. Okay? So, there you have it. That's how instruments use wave reflection to create the vibration within the string and create the sounds that we hear as the energy of the vibrating string. Remember, there's a wave in the string, there's a wave in the tube that then passes out into the air, that then affects the air around it, and then we hear that energy through our ears. Okay? So the wave properties, the wave characteristics of the frequency and the wavelength are determined by how quickly the wave is moving back and forth through the physical dimensions of the thing that's vibrating for that wave to happen. Okay, for a string, that the speed of the wave in the string depends on the tension and the mass per unit length of that string. Okay, the thicker the string, the slower it's going to move, so the lower the frequency it has. For windpipes, the frequency that's produced is based upon the length of the tube. Okay, that creates the wavelength, as we saw, and it also depends on the speed that sound can have at the given air temperature. The higher the air temperature, the higher the sound is going to be produced, which is one of the reasons why wind instruments, players of wind instruments, need to constantly remember to be checking their notice I'm a trombone player, so I'm tuning slide back here. Okay, the trumpet players, you got to be doing it off of the end. For clarinetists, they're always changing slightly up and down. For a flutist, the same thing. You have to be constantly doing that, because think about it. What's the temperature of your breath coming out of your mouth? It's close to body temperature. Eventually, the air that's inside your instrument, notice trombone thing going on here. The air that's inside your instrument is going to get warmer than the air outside. And so you have to remember to retune yourself to that. All right. The fact that the ambient air temperature inside your instrument is different from the air around you. Okay. So you may tune up at the right way at the beginning of the concert, but halfway through the concert, you're suddenly going to be sharp compared to everybody else because your air temperature got higher, the speed of sound is higher, so you're producing a higher frequency with the air inside your instrument than you are otherwise. Okay? I hope you enjoyed this, and I will see you the next time online to discuss what we've talked about here. Have a great one, and this is your friendly heavy physics teacher signing off once again for college physics.